All right, so in chapter 23, you'll find that we've pivoted rather abruptly from the intense mathematics and integration from chapter 22. Right now in chapter 23, which is on Gauss's law, is more conceptual, and we use symmetry to try and solve the problems and not rely necessarily as heavily on math. Okay, there's still some math, but not quite as much. Okay, so what I have here is a spherical surface. It's closed, meaning there are no holes in it. And I'm going to draw some electric field vectors from the left to the right. Let's see, let's draw one going across, and whoops. Let's see, it pokes through right there, for example. Okay, another one goes through the equator, like that. Another one may come in the foreground, maybe like that, and then a fourth one skims along just the bottom, okay, just barely tangent to the bottom surface, okay, or the bottom point, if you will. All right, so thinking of this spherical closed surface as a whole, if we were to divide the left side and the right side, right, thinking left and right, I didn't do that symmetrically, oh well. There are the same number of field lines going in on the left side as there are coming out on the right. And there has to be if this is a closed surface with no holes, right? That is the crux, is the nature of what electric flux is, right? You can think of flux as how much of some substance or how much stuff is passing through an area. I know we have a volume here, but this volume has a surface area, and that's what we're worried about. So electric flux is, well, the amount of electric field passing through one area and out the other, right? So overall, the net electric flux is the sum of what's going in and what's coming out, right? If it's a closed surface, it should be zero. So let's take those dots away. So every little point that the field pokes, we can have a little dA. Okay, well, I didn't draw that very good at all. Okay, every tiny little bit of area we can call dA, right? That's the differential area. We can write that another way. Say dA, that's the magnitude, and it's in the direction normal to the plane at that location. So we can say dA, it's in the direction of in hat, right? The normal. You can think of normal as perpendicular, same thing. So at the risk of drawing too many lines in that tiny space, that normal vector right there is perpendicular to the plane at that position, right? Perpendicular to the surface. I can draw another normal vector over here that's also perpendicular, and that has, we can assume the same sized dA, but the normal direction is in another direction, right? It's different to the first one I drew. Similar, that tiny bit of dA has a normal vector going that direction. Okay. What I haven't drawn, oh, sorry, I should do the other two. At the very bottom, the very south pole, if you will, that dA points straight down. Okay. And on the left side here, where that electric field is going in, that dA actually points down and to the left. And so the relationship between these the vectors, the dA vectors, and the electric field, which is always in the same direction, Well, that relationship we can say, well, there's an angle in between each of them. Right? That's 90, and that is its own angle, theta. I really shouldn't be drawing those angles as theta, 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 because if you think about it, this electric field is continuously bombarding this surface at every possible position, assuming it's a continuous field. And so that means there's really an infinite number of dAs, which point in an infinite number of normal in-hats, right? There's actually some coming towards us. I can't draw three-dimensionally, right? Towards us, boom, right there. And so if we think about this figure or this surface as a whole, as one, well, the number of field lines going in has to equal the number of field lines going out, yes. And so the net electric flux overall is 0. What goes in must come out. And we need an easy way to relate the flux to all of these normal or in-hat vectors. We need a way to relate it to all of the different angles. And the easiest way to do that is to write an expression, like this, right? The net electric flux, phi sub E, is the relationship between the electric field and area, right? Or we can write that as, since we don't just have one area vector, we should write that as dA, because that takes into account all of the possible dA orientations, right? This relation right here is the mathematical way to explain how we take into account the relationship between the electric field and every possible orientation for dA. Okay? And this is the net flux, right? It's a relationship between the amount of electric field passing through a surface at any point.